All right, for number 50, we are given the derivative graph and asked to find the original function and the second derivative function. So, on the derivative graph, I can see positive and negative values, and I can also see zeros. I have zeros at 0, and maybe that's 9. And so I can see on the derivative graph that I have negative values to the left of 0 and to the right of 9. So my original function is going to be decreasing in those two areas because the derivative graph is positive between those two intercepts. My original function is going to be increasing in those areas, or on that interval from 0 to 9. Okay, so my original function is decreasing from negative infinity to 0, and then again from 9, let's say, to infinity. My original function is increasing between 0 and 9. And that's based on the derivative graph being positive versus negative. So positive in that center interval, original graph must be increasing. Negative to the left and to the right of that center interval, original graph must be decreasing. The derivative is equal to 0 at 2 points. Those are most likely going to be extrema. So relative mins, relative max. So if my original graph is switching between decreasing and increasing, that means it's coming down and going up. I'm going to have a relative min somewhere. I don't know where the relative min is going to be, so I'm just putting it right there. And again, I don't know scale-wise where this value is going to be, so I'm just picking a point and saying that's going to be my relative min on my, I'm going to get blue, keep my original function in blue for this problem. Put a blue box around that so we can keep that in check. Okay, so my original function is going to be in blue, my derivative's in black, and then my second derivative, when I do that, I'll do that in red. I have another relative extrema because I'm going to have increasing to decreasing, so it's going to be going up and then down. So let's say I have a relative max at that point. And again, I don't know where the relative max is, but we're just going to use that for now. So that's just based on increasing and decreasing, or I should say based on the first thing in our chart of positive, negative versus 0 for my derivative graph. I can also tell that my derivative is increasing versus decreasing. So my derivative graph is increasing from negative infinity to 4, maybe a little bit past 4. I'm just going to say 4 for now. And my derivative graph is decreasing. So if my derivative is increasing versus decreasing, okay, these down here, I'm going to put those in blue just to show we're talking about the original function, f of x. To the left and right of the red line, to the left of the red line, the derivative is increasing. To the right of the red line, the derivative is decreasing. So when my derivative is increasing, my original has to be concave up. When my derivative is decreasing, my original has to be concave down. So we're going to have concave up right here. Extend this red line all the way down. So my original function is going to be concave up from negative infinity to about 4. My original function is going to be concave down from about 4 to infinity. And then also where that changes between concave up and concave down, right? We have an inflection point, which is happening at the extrema of the derivative. So the extrema of the derivative is giving me an inflection point on the original function. So there's a relative max here. It looks like it's about 4, 20. That means I'm going to have an inflection point at x equals 4, or about 4 somewhere. Okay. So most likely my curve, since my my derivative is a quadratic function, or at least looks like a quadratic function, my original function was probably a cubic. And so I know that it's decreasing to this point, then increasing. Notice on that entire interval I just drew, it's concave up, then it switches to concave down, still increasing, and now decreasing. So my original function could look something like that. I switch between concave up and concave down at the inflection point. I have a relative min, where it switches between decreasing and increasing, and a relative max, which switches between increasing and decreasing. And that's all just for the original function. Now I want to graph the second derivative. So I did add some rows to my table to continue the same relationship. It's just this relationship, but then moved over from the first and second columns to the second and third columns. If you had a third derivative, you could tell if the third derivative was positive or negative. So again, I'm going to look at where my derivative graph is increasing versus decreasing. Right, it's increasing to the left of the vertex, so my second derivative is going to be positive. Then it's decreasing to the right of the vertex, so my second derivative is going to be negative, with that relative extrema at 420, so we're going to have a 0 on the second derivative. Looks like I'm going from cubic to quadratic to linear. So the second derivative is going to have a 0, where they're on the same x value as the relative extrema. So I'd graph my second derivative in red. We know the second derivative is going to be positive and then negative, because the derivative graph is increasing and then decreasing. And so it could look something like that. Again, we don't know the slope of the second derivative graph, but I know that it's going from, I know that it's decreasing the entire time, and I know that it's positive and then negative, because the derivative graph was increasing at first and then decreasing. So the second derivative switching between positive to negative. I also know that the derivative graph is concave up the entire time. not concave up, sorry. Derivative graph is concave down. So I know that the second derivative has to be decreasing the entire time. So my second derivative graph, move this close to the line. There we go. So that's how you could graph the original function and the second derivative.